Hello, welcome back to this unit, please. Welcome back, folks. So, in the last unit associated with chapter 26, we saw how to combine resistors in series and parallel, and that was a good thing because we can actually take simple enough configurations of resistors in series and parallel and basically find their equivalent resistance. We can also solve for the circuit, which is equivalent to finding all the currents in each and every resistor and all the voltages across each and every resistor. But it actually turns out that there are some problems for which it is very difficult or impossible to just use the combination rules for series and parallel resistors to find all the currents in a circuit. In such circumstances, we actually have to use Kirchhoff's rules. So we have to learn about Kirchhoff's rules and teach ourselves how to use those rules. And Kirchhoff's rules is very important. So Kirchhoff's rules is so important that I will guarantee that on at least some midterm or somewhere you will have a big 20-point question associated with Kirchhoff's rules, which will actually span this unit and the next learning unit. And I will promise you that I will eat my hat if you don't see such a big test problem somewhere or the other. I don't have a hat, but I'm so sure of the situation that I promise you that I will eat my hat. So with that, let's go ahead and study Kirchhoff's rules and study them really well because they're really important. They're going to show up guaranteed somewhere or the other. So let's go ahead and understand Kirchhoff's first rule, which is his junction rule. What it basically says that if you have a junction like the one shown out here in the figure, and if you have a current I1 coming in and a current I2 and I3 going out, then you can actually say that the sum of all the currents coming into and out of a junction must be equal to 0. Now with that, you have to have a convention, of course, so you would actually say that I1, for example, is treated positively because it's coming into the junction, and I2 is treated negatively because it's going out of the junction, and I3 is treated negatively because it's going out of the junction, and therefore this is equal to 0. Or equivalently, you could just say I1 is equal to I2 plus I3. As long as you keep track of what is coming in and what is going out and how you balance them, everything will be fine. So this is Kirchhoff's first rule. It's called the junction rule, and it basically pertains to the fact that the amount of charge that is contained in any situation is a constant, and so we're basically conserving the amount of charge coming into a junction and going out of the junction. So with this, we go on to Kirchhoff's second rule. But before we do that, let's go ahead and actually make a little mechanical analogy to water flowing in a pipe. So in that case, you have the amount of water flowing into this junction out here being equal to the sum of the water flowing in the two pipes that are leading the water out of the junction. So in that situation too, you know that the number of water molecules is conserved, and so the amount of water molecules coming in from the left is equal to the amount of water molecules going out in the two pipes on the right. So that is again an expression of conservation, and now we actually have a somewhat deeper appreciation of the fact that Kirchhoff's first rule, namely the junction rule, is an expression of conservation of charge in a circuit. So with that, let's go ahead and move on to Kirchhoff's next rule, which has to do with Kirchhoff's loop rule. So the loop rule basically says that the potential differences across all elements around any closed circuit loop must be 0. Let's take an extremely simple circuit loop like the one that we have seen in the previous chapter. In fact, this one is borrowed right from the previous chapter. And we basically understand that in this circuit, we have a situation where as we go from A to B, we have a voltage rise across the battery, which is given by the EMF of the battery. And notice that EMF is oftentimes denoted with a curly E. So we say that we have this voltage rise across the battery as shown by the rise in the EMF. Then no change till we hit the point C in the circuit, which is this point out here. So going from this point to this point we had a voltage rise of E. Then we have no change in the voltage going up to C. But in going from C to D, we're actually going across the internal resistance of the resistor. And we know that if we traverse a resistor in the direction of the current flow, we will actually have a voltage drop across it given by I times R. And so we actually see that this voltage drop is taking place. So we actually put minus I times little r, where I is the current in the circuit. That brings us to the point D. And of course, from the point D to the point E, we go through the circuit with no change in any voltages. Then we're at the point E, and we try to go to the point F. As we go from E to F in the circuit, so notice, of course, that we're traversing this circuit in a clockwise, direction. So we're traversing the circuit in a clockwise direction, and we're now going from E to F. As we go through E to F, we're going through a resistor in the direction in which current is flowing, and we therefore see that we're going to have a voltage drop given by another minus I times the resistance of the external resistor, which is big R. And that brings us to the point F, and from F to A, we can actually go ahead and have no voltage change in this circuit. So we started at A, and we went ahead, we made a complete circuit around the loop of around the current carrying loop that we've been shown in the figure, and therefore we say that the total voltage change is actually equal to 0. Now this can actually be expressed even in terms of energy considerations. So let's go ahead and erase this figure and make some energy considerations to show that Kirchhoff's law is basically an expression of energy conservation. So let's go ahead and ask what happens if a current I flows through the battery E, and the answer is that we have an amount of power that this battery supplies, which is E times I. Now this current I is also running through the resistor, and so the power drained by the resistor is always given by minus little r times I squared. This same current flows through the external resistor, the big R, and therefore we have an amount of we have an amount of power drained in that external resistor, which is given by minus big R times I squared. And that basically means that the total power supplied by the battery minus the power power wasted by the resistors as heat is actually just balanced. And so that tells us that this should be equal to 0. Now notice that if I go ahead and cancel off one factor of I in here, I obtain exactly the same equation as the one that we obtained before, which gives us the idea that in fact Kirchhoff's loop rule is basically a statement of energy conservation. In other words, if we applied energy conservation to this equation below, we got the same rule as the equation above, which said that the change in potentials across all the circuit elements taken together in a loop should actually equal to 0. Okay? So to apply the loop rule, you must essentially choose a direction in which you traverse the loop. And we will essentially expound on this issue in a minute. But now let's go ahead and first train our eyes so that we understand how to identify loops in circuit elements. So say schematically that we have the circuit element shown in the left top situation. Then we have a single rectangle, and we see that we could actually traverse this rectangle clockwise or counterclockwise, but we essentially have a simple single circuit element. So this is a situation where you have one loop and you basically also have one independent loop. Now let's go ahead and look at the second circuit element that is shown in the middle. Schematically, this looks like one loop that you could traverse like this. It also looks like another loop that you could traverse, and I'll show it in blue now. But you could also, in principle, combine these two loops and get this purple colored loop, which you can have like this. So we can now go ahead and ask, how many total loops do we have? And the answer is that we indeed have 3 loops in this circuit. However, which are the independent ones? The answer is that you could actually, in principle, combine the red and the blue loop to get the purple loop, and so we only have two independent loops in this circuit. Now let's go ahead and focus on the figure in the top right, and we realize, of course, now that we have one possible loop, another possible loop, a third possible loop, and these are the simple choices. But in principle, I could actually have the left two simple loops combined to obtain a loop like this. Alternatively, I could combine the right two simple loops to obtain a loop like this. Alternatively and equivalently, I could also go ahead and combine the entire situation and obtain a purple loop like this. So how many loops do we have? The answer is we have 6 loops, but out of the six loops, we have only 3 independent loops because we can combine the loops in various ways. Now I'll leave the figure in the left lower panel to you guys to basically think about, and you guys can think about how many total loops you have and how many independent loops you have in the circuit shown out here. And of course, you can actually also find the junctions in this situation. So in the left upper panel, there are no junctions. In the left middle panel, this can be a junction and this can be a junction. That's where the current comes in and forks. In the right upper panel, we have a junction here and a junction here. Likewise, we have a junction here and a junction here. So those are opportune places where you'll apply the Kirchhoff junction rule. Of course, realistically, you would not apply the junction rule to each of those junctions because you will have independent information only coming from a few of those junctions. So with that understanding, we can now go ahead and talk about the other issue that we raised in the previous transparency, which is the direction of current flow. So imagine, if you like, that we still have a simple situation where we have out here the battery number 1, which has an internal EMF of E1 and an internal resistance of little r1, and we have this battery number 2 stuck out here, which has an internal EMF of E2 and an internal resistance of r2. Let's go ahead and start at point A and apply Kirchhoff's loop rule as we go through this circuit in a clockwise direction. So we start from A and we go to B, and we realize that in doing so, we have a voltage drop across the resistor R1, which is just given by minus I, the current in the circuit. And notice there's only one current in the circuit because there's only one loop. So we have minus I times R1 as the voltage drop as we go from A to B. As we go from B to C, we're again traversing the resistor R2 in the direction of current flow, so we have a voltage drop given by I times R2. When we come to C and try to go to D, notice that we're traversing the battery number 2, but we're traversing the EMF of that battery in a direction that is opposite to the actual conventional negative to positive direction in which we would traverse the battery. And so instead of having a voltage rise from E2, because we're traversing E2 from the direction C, from the point C to the point D, we actually have a voltage drop across E2. So we write E2 negatively. Then we go through the internal resistance of battery 2, which is the little r2, and therefore we have a voltage drop of minus I times little r2. Then we come to the point E, and we go from the point E to F, essentially traversing resistor R2, and so we have a voltage drop of minus I times R3. I'm sorry, I should have said that we go from E to F, essentially traversing the resistor R3. And then we essentially come to the point F, and going from F to G, we're basically going through the EMF of the battery in its conventional direction. So we have plus E1. And then we're going through the internal resistance of battery number 1, which means that we have a further voltage drop of I times little r1. This total thing should be equal to 0. If we go ahead and solve for the unknown, which in this case is just the current I in this single loop circuit, then we come up with this answer. Now the answer mathematically is per se not as important as understanding what is going on in this situation. So imagine, if you like, that current I is flowing in the direction that is shown. In other words, let's say that we picked a certain direction for current flow as shown in this direction at the top, and therefore we say that the current is truly flowing in the circuit in a clockwise direction, not counterclockwise, I'm sorry, clockwise. And so we say that the current is truly flowing in the circuit in a clockwise direction. Therefore, we will actually realize that the battery E1 is giving up an amount of power to the circuit that is given by E1 times the current I. However, ask yourself what is happening in the battery E2. In the battery E2, this same current is actually flowing in the opposite direction, which means that the battery E2 is actually absorbing an amount of energy from the circuit that per unit time that is given by E2 times I. So the battery E1 is donating an amount of energy every second that is given by E1 times I, and energy per second is basically units of power. However, the battery E2 is actually draining off energy every second, and the amount of energy that it drains is given by E2 times I in every second. Therefore, the amount of power that it drains is given by E2 times I. And so we realize that E1 gives away power to the circuit. On the other hand, E2 actually absorbs power from the circuit. In other words, it sucks the power in. Now, if battery number 2 is a rechargeable battery, what you'll have is a situation where battery number 2 is getting recharged as the current flows in a clockwise direction in the circuit shown. Battery number 1 is actually donating its energy in order to help battery number 2 to get recharged. And that's exactly how batteries get recharged one from the other. So if you charge a battery up using another battery, in this case, if you charge battery 2 using battery number 1, then battery number 1 is losing energy, battery number 2 is gaining energy. Now that is true as long as a battery is rechargeable. If a battery is not rechargeable and you still try to put it into one of those chargers that will charge a battery up, then you actually risk a situation where the battery can get so hot because of its internal resistance, and there is nothing that causes it to get charged up, and so the battery can essentially split its guts, blow out, spill acid all over your carpet. Not a good sight. And that is the point. That is actually the reason why they tell you that in these rechargeable things that you can buy at the store, you should never put a battery that is not rechargeable. But this actually gives you an idea of what is going on. Now, actually, let's go ahead and imagine also a situation where we thought initially that the direction of current flow is in the direction shown, but I turned out to be a negative number. In that case, we would actually say that the battery number 2 is donating an amount of energy given by E2 times I, and the battery number 1 is actually getting recharged and getting an amount of power um, given by E1 times I. So this would happen if we perchance chose I to be originally in the clockwise direction, but I turned out to be negative, which basically means that I is actually flowing in the opposite direction, not in this direction in the circuit. So we have actually covered all the situations, and we've actually shown something very important, which is to say that if we choose the direction of the current I and then we do the mathematics and the I turns out to be negative, then what we've shown out here tells us exactly what we have to do, namely, don't panic, don't worry, just remain calm and realize that you chose the direction of current flow to be opposite of what it is, and so you can actually go ahead and at the end of the problem you can backtrack and choose the direction of current flow and say that the direction of current flow is opposite to the direction that you have chosen out here. So this is a very simple situation where if we had chosen I to be going in the opposite direction, we could still have salvaged the situation. No need for panic. Okay? So with this, let's move forward And let's go ahead and put ourselves through this very, very complicated circuit, which has a ton of resistors and a ton of batteries in it. Let's go ahead and ask you to find essentially the current flowing through the resistor R. Notice that in this problem, and we say that it's a mind bender to begin with, we're not asking you to find the current in any other circuit device or anything else. We're just asking you to find the current in the resistor R. So if you think about it, there has to be some sort of catch, okay? And we realize that if we send the path, we can choose any closed path to assert Kirchhoff's law. But if we send that closed path through any resistor, we realize that we would actually then be obliged to find the current in that resistor. So what we do is we try to be a little sneaky and choose a path that is such that we're only going through legs of the circuit that go through batteries. So we traversed this battery, and then we have traversed this battery again in the conventional direction. Then we move on here, 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 and then we traverse this battery. Again, we've traversed this third battery in the conventional direction. Then we come out here and we keep going in this direction, and we're traversing this battery, the fourth battery, in the opposite direction. And that brings us back to this point. So we've essentially completed a red loop. And across this loop, we realize that since we're told even to begin with that all resistors and all batteries are identical, we'll say that when we traverse this first battery, we had a voltage rise given by E. When we traverse this second battery, we had a voltage rise given by E. When we traverse this third battery out here, we had a voltage rise given by E. And when we traverse this fourth battery in the opposite direction to the conventional direction, we got a voltage drop, which is E. And that should in fact be balanced by minus I times the current flow in this direction in the resistor. So this is I, the current in the resistor. So we have minus I times R if we've chosen the current going downwards, and this is equal to 0, which immediately tells us that we have IR being equal to 2 times E, because we have 3 plus E's and we have a 1 minus E, so that's 3 minus 1, which is 2. And so we have IR being equal to 2E, and therefore I as being equal to 2E divided by R. So in such a mind bender, you essentially want to back off a little bit and find the little clever trick that is in the circuit rather than actually going ahead and trying to solve the circuit in a complete and perfect way. So now let's go ahead and look at the next problem, which essentially asks us to find the charge on the capacitor that is the one shown out here. We might be able to take up this problem in class, but I'll urge you all to think about it and think about which paths you could choose so as to obtain a good path that will allow us to come back to this original capacitor with minimal traversals of other batteries and perhaps with no traversals of any other capacitors. So go ahead and think about that, and we'll go ahead and address this in class. Here's another little Quizler for you. It basically tells you that you have a tetrahedron. The sides of this tetrahedron, there are 1, 2, 3, 4, 5, 6 sides to this tetrahedron and 4 vertices. So let's go ahead and label the vertices A, B, C, and D. And we're told that each of these sides of the tetrahedron has 10 ohm resistance. So we have 10 ohms between A and D. We have 10 ohms between A and C. We have 10 ohms between C and D. We have 10 ohms between A and B. We have 10 ohms between C and B. And we have 10 ohms between B and D. We're asked to essentially imagine a situation where current is going through vertex A and coming out through vertex B. whereas to go ahead and find the solution to this problem. Now, of course, in all these topologically complicated problems, a direct assault on the problem or even a brute force Kirchhoff law assault on the problem is in some sense counterproductive. But remember that if I go ahead and slice this circuit through the line AB and coming out on the slice through the midpoint out here, then the situation is completely symmetrical, which means that the amount of current flowing from A to B can be written as I1. And from the symmetry of the problem, there's an amount of current I2 going from A to D. There's an amount of current I2 going from A to C. Okay? And from the symmetry of the problem again, there's an amount of current I1 coming from A to the vertex B. So this current is I1. Now, what I want you to realize is that if this point A is at a certain voltage, then the point then the point C and the point D will both be at the same diminished voltage because we're sending the same current I through a 10 ohm resistor on the leg AC and also on the leg AD, which means that C and D will have some reduced voltage, of course, but they'll have the same voltage because the voltage from A is reduced by the same amount at D and C. So the voltage at D is just equal to the voltage at A minus 10 ohms times I2. Okay? The voltage at C again is equal to the voltage at A minus 10 ohms, which is actually flowing through the leg AC, and that leg AC has a 10 ohm resistance and it also has a current given by I2. So let me go ahead and clean up this end of the diagram a little bit, if I may, so that things are a little more visible. Okay, so I'll actually go ahead and now label this point A, and I will call this current I2 from the leg A to C. And we already have I2 nicely labeled from the point A to D. So we understand that from the symmetry of the situation, we have a current I1 through the point A to B, and we have I2 from A to C and I2 from A to D. And we also understand that there's no voltage difference between the points C and D. If there is no voltage difference, then the bottom line is that along the leg that connects C to D, there will be no current flow. So the current flow out here is actually equal to 0 along the leg going from C to D. That means that all the current I2 that flowed from A to C is also going to flow from C to B. So we have I2 flowing in the leg given by C to B. Likewise, all the current that flowed from A to D is not going to flow from D to C, but rather is all going to flow from D to B. And so we have a current I2 again going in the leg given by D to B. And so we have a very simplified situation where we can draw the simple situation like this. So imagine that this is the point A, this is the point B. I have a 10 ohm resistor out here, and I have a current I1 going from A to B. I can draw the same current I1 out here. Now, let me draw the point D out here. I can actually say that from A to D, I have a 10 ohm resistor, and I have a current flow from A to D that is actually equal to I2. And from D to B, I have another 10 ohm resistor, and the same current I2 is flowing from D to B simply because I have proved to myself that the voltage at C and the voltage at D is the same, and if the voltage across the two ends of a resistor are the same, then no current flows through that resistor. So there's no current flowing through the resistor that connects C to D. Now I can also draw the point C out here. So let me call this the point C, and I know that between A and C I have a 10 ohm resistance, and I have a current I2 flowing in this direction, and none of this current I2 which comes to C will actually go to D. Instead, all of it will indeed go to the point B. So I know that I have I2 also flowing from C to B, where I also have a 10 ohm resistance. So I see that I have a situation where now I can draw an equivalent circuit where I can say that I'm starting at point A. Okay, I have one resistor with a resistance of 10 ohms, which takes me to the point B. I also have another resistor of 10 ohms out here, which takes me to the point C, and from the point C I have another resistance of 10 ohms which takes me back to the point B. So this is another 10 ohm resistor, and I also start at A, and I can go towards D through a 10 ohm resistor. So I have another 10 ohm resistor out here, okay, and that gets me to the point D out here, and from the point D out here I have another 10 ohm resistor, and that 10 ohm resistor gets me back to the point B. So I see that I can go ahead and take the top two resistors, and these two guys are in parallel, so I can effectively go ahead and say that I'm starting at A out here. I have a resistance of 10 ohms out here, okay, and I'm getting to the point B out here. The top two resistors taking me from A to C and then from C to B give me an equivalent resistance of 20 ohms. Okay, so I have 20 ohms out here, and then starting from A and going to D and then going from D to B, I have another two 10 ohm resistors in series. So two resistors of 10 ohms each gives me an equivalent resistance of 20 ohms, and that brings me back to B. So I have 20 ohms, 10 ohms, and 10 ohms, all of them connected in parallel. And so I should actually go ahead and do 1 over 20 plus 1 over 20 plus 1 over 10 in order to find the equivalent resistance. So let's just go and do that where we have a little bit of clean space. So we have 1 over Req is equal to 1 over 20 plus 1 over 20 plus 1 over 10. So 1 over 20 plus 1 over 20 added together gives me 2 over 20, which is just 2 over 1 over 10. And then I have another 1 over 10, so that actually gives me 1 over 5. Okay, so Req, the equivalent resistance, in the parallel situation, I know that the equivalent resistance should be smaller than the original three resistances that went in. So this Req is just an equivalent resistance of 5 ohms. Okay? So this tells me exactly what I have. I have an equivalent resistance of 5 ohms, and then you can actually go ahead and find the currents in each of the legs of this circuit, because you know exactly how to kind of peel back and find the resistance in each of the legs, and therefore find the current flow in each of the legs and work backwards. So you can do part B, namely find the current in the battery by yourselves. We've done part A, which is to find the equivalent resistance across the points A and B. Okay, so with that, we have essentially gone ahead and done quite a few tricky problems that show us Kirchhoff's laws in many interesting, unique ways. Now, the reality is that we're not going to trick you that much on a test or an exam. We're going to essentially expect, nevertheless, that you'll be able to do problems that require kind of a linear application or a logical application of Kirchhoff's laws and apply these laws in a sensible way. Now, to help you apply these laws in a sensible way, we have set up a set of 7 or 8 tips. We want you to go ahead and remember these tips, because if you follow these tips in a completely logical way, you'll be able to go ahead and solve any typical, nice, simple, flat, uncomplicated Kirchhoff law problem that we might give to you. Okay, so with this, the first tip says replace any combination of resistors in series or parallel by its equivalent resistance. So whatever you can simplify by using your laws of series or parallel resistor combination, you just use those laws and simplify that part just to begin with. Then, in each branch of a circuit, choose a direction for the current flow. Okay? At the end of the problem, if that number for the current flow in that circuit turns out to be negative, it means that you don't panic. It means that you just agree that in that case, the current flows in the opposite direction from the direction that you chose. Okay? In other words, do not be afraid of choosing a direction for the current flow. As long as you apply the math and as long as you apply the rules correctly, everything will come out well in the end. Okay, so with this idea, we go through the first 2 tips. The third tip actually begins to teach us about how to deal with resistors if we're traversing them in a certain direction or in another direction. So imagine figure A, which says that we're traversing this resistor from the point A to the point B. And we've drawn the current direction to be going from left to right. In that case, we say that we're traversing the resistor in the conventional direction, and in the conventional direction, the resistor actually provides a voltage drop. So if we're going from A to B, if we're traversing the circuit from the point A to the point B, and the direction of current flow across the resistor has been shown as out here, from left to right, then we actually say that we have a voltage drop across that resistor. However, focus now on figure number B. It says that we're traversing this resistor still from the point A to the point B, but in doing so, we're traversing it in a direction that is opposite to the direction of current flow. The current in this case is flowing from right to left. And so we therefore say that this resistor, when traversed in the direction that is opposite to the direction of current flow, will actually give us a voltage rise given by I times R. So this resistor shown in figure B gives us a voltage rise simply because we're traversing it in the direction that is opposite to the direction that we've shown for the current flow. The situation with batteries is kind of very similar. So let's go ahead and look at this picture C. Picture C on the top basically says that you're traversing the circuit from the point A to the point B, and you're traversing it in the conventional direction across the battery. Therefore, this battery, because you're going from its negative terminal to its positive terminal, actually gives you a voltage rise. Now imagine that we're focused, or imagine that we have a situation analogous to figure D. In that case, we're still going from the point A to the point B, but now we're traversing the battery from left to right. And in doing so, we're going from its initial positive plate to its negative plate. And when you do that, you actually have a voltage drop across the battery, and that voltage drop is given by minus E, where E is the voltage of the battery. So it tells you that if a battery or a source of EMF is traveled in the direction of the EMF, in the traditional direction of the EMF, then the potential difference that you add in is a positive potential difference. Okay, so this is the conventional direction in which you think about batteries being traversed. But if perchance you have to traverse a battery in the opposite direction, namely going from the plus plate of the battery to the minus plate of the battery, then that battery should count negatively and it should give you a voltage drop given by minus E. With that, we're now ready to polish off this unit by basically realizing that we have also to apply the junction rule at each and every junction. Oftentimes you will find that not each and every junction is needed, but applying the junction rule to a suitably small number of junctions allows us to dramatically reduce the number of independent variables that we will have to solve for the current flow in the largish linear system of equations that gets developed. By the way, to solve Kirchhoff's law problems, you will have to be good at solving problems where you have uh, two linear systems in two independent variables, or even perhaps in an off chance, three linear systems with three independent variables. These days, you can, of course, dump that into your calculator and ask the calculator to invert for you, but you will still need to be very sophisticated in how you set up the linear equations and set them up correctly so that the calculator can solve it for you. Uh, so if you're applying a loop rule, do not apply it to all the loops in the circuit. Apply it only to the number of independent loops in the circuit. And remember that you can always have more loops than you have independent loops, so choose your independent loops wisely. And then one thing to remember is that you can check your results. So you can actually go ahead and set zero potential at any point in the circuit and then traverse all the loops in that circuit and add up all the potentials as you traverse the loop in each loop in that circuit, and the net potential change coming back to the original point should indeed be zero. So this gives you a strategy for checking your Kirchhoff law problem. So with this, we've studied quite a bit of interesting things associated with Kirchhoff's laws. We've essentially reviewed Kirchhoff's junction rule, which deals with what you do to the current that is coming into or going out of a junction. We've also studied Kirchhoff's loop rule, which basically tells you how to deal with a situation where you have a loop being traversed. We've taught ourselves how to identify independent loops, and we now know that we have only to apply the loop rule to the number of independent loops in the circuit. We've also gone ahead and studied about how batteries are charged or discharged, namely how a battery provides power to a circuit or how a battery absorbs power from a circuit. If, of course, the battery is rechargeable, then it can absorb power from the circuit in a very nice way and thereby get recharged in the process. If a battery is non-rechargeable and you've stuck it into a rechargeable unit and you've stuck that into a wall outlet, expect a nice little explosion at some point. You might have a little acid spilt on your carpet. That's your problem. Then we've actually gone ahead and gone through these very important tips. I cannot stress the importance of these tips, namely tip number one, replace any combination of resistors that you can in series and parallel by an equivalencing. And in each tip number two, in each branch of a circuit, choose a direction for the current, and don't be afraid if that number turns out to be negative. It just means that the actual direction of current is opposite. If you traverse a resistor in the conventional direction, namely along the direction of current flow, you get the conventional voltage drop across the resistor. If you traverse the resistor opposite to the direction of current flow that you've set to begin with in your circuit, then you should treat that as a voltage rise across the resistor. A battery traversed in the conventional direction, namely from its negative plate to its positive plate, gives you a voltage rise. But if you traverse a battery from the positive plate to the negative plate, which is the non-conventional direction if you think about it, then you get a voltage drop. And then these last three tips, which deals with the fact that you have to choose junctions and divide the current judiciously, keeping, of course, the minimum number of independent variables. If you have proliferation of independent variables, then that's also not good. because you're solving a very big system. Maybe your calculator will choke in solving that system. And then we went actually and we actually saw that we have to apply the loop rule to the independent loops in the circuit. And after we've obtained a result, we have to ensure that our result is correct. So if you want, if you have time on a test or something, you can always go ahead and check your result and make sure that the total voltage change across each loop of your circuit should exactly be equal to zero. That gives you a good confirmation that you've solved the Kirchhoff law problem correctly and you've been paid off for your efforts in this section. In the next section, what we're going to do is essentially do practice, practice, and practice, and make sure that we understand how to solve Kirchhoff's law using various examples that we'll put in front of you. So with that, I'll thank you very much for your attention and look forward to seeing you in the next unit. Thank you very much and see you all soon.